So let me quickly introduce myself. My name is Frans van Buul. I spent my time at Axonic divided over two things, a little bit of product development in Java myself, but most of the time I'm telling the world about our products and services. I'm known internally as not a sales guy exec. That's what my mug says. So let's quickly position Axonic and Axon Framework, because Axonic is still a very new company. We were founded in July of last year, so a little more than 6 months ago. Axon Framework has been around for a long time. It's an open source Java framework for event-driven microservices, building around concepts like CQRS and event sourcing, which is particularly relevant for this webinar. It's very mature. We have more than 600,000 downloads. And Axonic was founded to further support that framework. And we're doing that in two ways. We're developing some commercial software offerings that can work on top of the open source. And we provide things like support, training, and consulting. Zooming in on those software products, we have two of them available now. AxonDB, which is the topic of this webinar, formerly known as Axonic Event Store. So if you participated in the beta testing of this product, then you might know it by that name, but we've renamed it, and I'll explain that later on. We also have an Axonic GDPR module. Some stuff on our roadmap is the Axon Hub. That will be the first thing. We're considering to create SaaS-based versions of our software products in addition to the on-premise delivery we have now. And we're also exploring monitoring and analytics. If you're on our mailing list, we will, of course, keep you informed of everything that's happening in those areas. But for now, we'll focus on AxonDB. The agenda for today, I want to start by talking about event sourcing and related concepts in general, just to set the stage. Then we'll, based on that knowledge, derive some key requirements that you would have for any type of event store. Then we're going to evaluate some pre-existing options and see if they meet the criteria for an event store. And we found out that they don't in general. So that's why we developed AxonDB. And we'll explain you about the architecture of AxonDB and which features it has. And then finally, if you want to get started with AxonDB, we'll tell you how to do that as well. First things first, event sourcing is all about events. So what exactly is an event? An event in this context is something that has happened. So it has happened at some point in the past, and it has a couple of important consequences that directly affect what an event store should do. So first of all, an event is conceptually immutable because it happened in the past, and you cannot change the past. So you cannot change an event either. And there's no such thing as an event failing. Events just are. A command can fail, but an event just is, and you can fail or succeed in processing an event, but the event as such just is. Events are not the same as messages. That's something, sometimes we see that message-driven architecture and event-driven architecture are used interchangeably. They're very different. Events are about things that have happened. Messaging is a style of integration where you use asynchronous couplings. Events lend themselves very well to be transmitted as messages, but they're not the same thing. And in a domain-driven design context, these events are business events. Like in general, events can also be things like mouse clicks, but unless you're in a mouse click business, that's not a business event. So events typically are order placed or something like that. And the entire idea of domain-driven design is that you represent such concepts explicitly in your application code as well. So those are the types of events we're talking about here. Event-driven architecture is one of the big trends for 2018, according to Gartner. And it's essentially simply a software architecture that promotes using events. And one of the reasons that this is really popular is that this works very well in a very connected world. It works very well with blockchain even. Having this past ledger of everything that has happened. You can feed events very well into machine learning and AI algorithms. So these events form the basis of many other cool applications. So that's why people are exploring it. If we look at event sourcing, and event sourcing is essentially a specialization of event-driven architecture. So I would argue that every event-sourced architecture is an event-driven architecture, but not necessarily the other way around. And the essence of event sourcing is that these events the notion of an event forms the heart of your persistence and data storage architecture. Now let's see what that is by looking at an example. First, we're going to look at e-commerce, an e-commerce example in a non-event source database. And then afterwards, we're going to look at the event sourced alternative to see the contrast. In this case, the database starts out empty, and a user of the web application starts a new order. So what's going to happen then is that you will store a new but still empty order in the database, or maybe you call it a shopping cart, but it's essentially the same thing. Then the user may add something to the order like sunglasses. You would see then that the database gets an update. So the database record has changed and the order now contains the sunglasses. Then you may add some Jimmy Choo shoes to this order. This example may also tell you who has invented the example. It was not me, looking at the list now. And the database would be updated again. Then there could be a shawl. And then before checking out, the user may decide to not buy these Jimmy Choos because they're really crazy expensive, and then remove them from the order. So then you would get a delete and an update, and the order would no longer contain the Jimmy Choos. And then the user may check out, and then the order would be fully confirmed. So this is a very natural way of working, which may seem so natural and the obvious way of doing it that you may wonder why I'm telling this at all. Now, with event sourcing, works quite differently. So let's go through the example again, but now in an event sourced way. The user starts a new order. We register the fact that an order was created, so that's an event. Then the sunglasses get added to the order. We register that event. Product added sunglasses. Shoes, the shawl. And then when the shoes get removed by the user, we wouldn't remove that product added event because events have happened. They are in the past and you cannot change that fact. But you can record the fact that the product was removed, so it should not be taken into account when fulfilling this order. And then the order gets confirmed. So this list of 6 events is now the contents of the database. So that's the essence of event sourcing. Now, this is obviously more complex than the old way of working without event sourcing. So the obvious question to ask is, why would you do this? It turns out that there are many reasons why this is great. And the most important reasons are actually business reasons. There are a couple of technical reasons as well. This has certain benefits about dealing with concurrency and replaying stuff. But the actual reasons are the business reasons. They have to do with the fact that historical data is valuable. So you don't want to throw that value away by overriding that data. And the historical value of data is essentially in 2 categories. So one is the historical value of being able to retrieve what happened in individual cases. So that has to do with auditing and compliance. And then there is the value of having historical facts about the data set at large. So that's where you have data mining, analytics, machine learning. And in this case, the sales manager of this shop would probably want to know what they could have done to make sure that this next time this user would actually buy the Jimmy Choos. Or you may send an email to these people saying, well, you're interested in Jimmy Choos and now we have a discount on them. Do you want to buy them at this price? So there's all kinds of stuff that you can do once you capture that history. And that's the main reason why people are using event sourcing. So an event store in an event sourced application is by definition the system that you use to store those events. So it's a database system. And in terms of implementation, it can be many different things. So what we see most often nowadays is that relational database technology is being used. So Oracle, MySQL, MariaDB, anything like that. Can also be NoSQL. Mongo is there the most popular choice. And then there is specialized event store technology. And AxonDB falls in that category. So that's how you should place our technology. This is also immediately the reason why we decided to rename the product. Event store is more like a category or a function, and to have that as the name of the product as well was very confusing. So now we're calling it AxonDB, which should be a lot more clear. If you look at the event store in the context, then the event store obviously communicates with the application. The application reads past events from the event store, and it appends new events to the event store as they happen. This works well for processing changes, for commands being sent to the system. But if the application would like to know all orders with a total value of more than 100 euro, that would be a very expensive operation, because the only way that the event store could execute that would be by replaying all events, taking into account what was added and removed from orders, so that wouldn't really function. And for this reason, event sourcing as a pattern is nearly always combined with another pattern called CQRS, Command Query Responsibility Segregation. And the idea there is that we still keep this application and event store communication that we had in the previous diagram, but we now only use that part to process commands, so to process actual transactions. But executing queries is not done directly on the event store, but instead we have some separate projection databases there, which may be in all kinds of technologies. And there is some projection logic that reads events from the event store, and then as a result of that makes updates to the projection databases. I'm telling you this because it's relevant in understanding what kind of requirements that you would have for an event store. So let's have a look at that. On a very high level, an event store needs to read events and write events. Those are the two basic things it has to do. Reading comes in a couple of flavors. So there's the case where you want to have all aggregates, all events for a particular aggregate, for a particular object, like an order. And that's the case that's relevant for command handling. But given that we're doing that CQRS thing, we also need to be able to read all events since a particular point in time without caring of a particular aggregate. So that's for creating those read models or projections. Events are very naturally time ordered, and when we read them back, we want them back in the same order as well, which may seem very obvious, but it's definitely not the way that a traditional relational database would operate. And then what we found out, and this was actually something we found out during the beta testing, is that people also sometimes need to do ad hoc queries. So in theory, you don't do direct querying on an event store because you would have your projections for that in a CQRS architecture, and you shouldn't do that directly in normal usage of a system because it would be too slow. But then again, during debugging of your application and when providing support for a production system, occasionally you just want to know what exactly is in my event store. Can I find an event with particular properties, all that kind of stuff? So that's something that an event store should support as well. On the right side, we obviously need to append events at the end of the event stream. There's a couple of things that we don't need to do, and that's important as well. We don't need to be able to insert events at a random point. We don't need to update events, they're immutable. We don't need to delete events because they're immutable and they have happened. It doesn't make sense to delete them, which means that it's actually not about writing events, it's about appending events, which is a lot simpler to do if you would have to implement a database system from scratch. Let's look at some more specific requirements than this. Switch to a different example here. This is about a bank account with a balance and a limit. The first event in the life cycle of a bank account would obviously be to create it. And then we deposit some money to the account, in this case 1,000. And then we withdraw some money from the account, 600. That's fine. But now suppose that the system is scaled out and there are multiple nodes that all operate concurrently. In this case, 2 nodes may at the same time be processing this withdrawal command. And if they both read the account in the same state, so after the first 2 events, then they both come to the conclusion that the current balance is 1,000. And one node thinks, well, it's okay to withdraw 600, and the other says, well, it's okay to withdraw 700, and they will both try to publish an event. Now, what should happen with event storage is that this will fail and thereby guarantee the consistency of this object by noting the fact that the sequence numbers are colliding. So there cannot be 2 events for the same aggregate with the same sequence number. So that's something that we would expect from an event store to validate that aggregate sequence number consistency. Another requirement I created this example as an investment account. So you can have some shares in this account or other securities, as well as cash. So you may have a command to buy some shares given the cash that you have. And then if the system is implemented in such a way that it does this with 2 events, so it would write down a withdrawal event for the cash as well as add event for the shares, then it's very important that both events are either committed both, or none of them is committed, because otherwise you would lose money or create money. In other words, you want atomicity when appending multiple events at once. Atomicity is the phenomenon on the append side, on the right side. Its correspondent requirement on the read side is that you have isolation, that readers only see events that are actually committed. And now that we're looking at the famous ACID acronym, let's add durability as well. Once events are committed and the application believes they are stored by the event store, then they should actually be stored and protected against loss. Another requirement has to do with one form of scalability. Suppose this bank account has been around for a long time, for 10 years or so. Then there will be a very large number of events stored with that account, may easily be thousands. Now suppose that every time you need to process a new transaction for that account, you need to replay all those events. That would start to have a performance impact. So there's a solution for that in CQRS and event sourcing. It's called snapshotting. So what you do every, say, for instance, 100 events, you create a new snapshot. So snapshot is like an image of the entire object, so the entire bank account as it is in that point in history. And you store that as well. Then whenever you need to access that aggregate, even though you do event sourcing, you don't need to replay all events. You just need to access the latest snapshot and then apply all the events to that snapshot that have occurred after the snapshot was taken, which can be a great performance enhancer if you have long-lived objects. If we take this into account into our requirements, what we see that it's not just about events, it's actually about events and snapshots. On the read side of things, so if we read events for an aggregate, there are actually 2 ways of reading. So one is to read the latest snapshot and then events that came after that. That's what you would be doing with normal command processing. But then for auditing purposes, you'd still want to have the option to read all events, period, without taking into account snapshots. Now, another scalability concern doesn't have to do with the individual aggregates, the individual objects, but with the event store at large. So let's not consider the individual bank account now, but let's think about the entire bank. Now, in this case, the number of events that you would have in your event store may easily be billions. In fact, we have that produce 1 billion of events per day. So the number may become really, really big. So what that means in terms of requirements is that on the append side, you need to have constant performance as a function of storage size. May seem obvious, but with relational database technology, you would see that append performance actually degrades as the data that's already stored grows. On the read side, what you want very specifically for event sourcing is that the system is optimized for recent events. Business processes, by their nature, tend to end at some point. If we take into account the web shop example again, once an order has been committed and delivered and paid, not much more can happen to it. So even though the events are still in the event store, the chances of them being accessed again are very small. Also, if you use snapshotting, then you would normally only access the events that came after the snapshots, but not the ones that came before that. So if you have an event store, you want to optimize it for reading recent events, and for instance, keep recent events in RAM rather than reading them from disk all the time, or keep the last few months of events on SSDs and store all the ones on traditional disks. All that kind of optimizations are reasonable to ask from an event store. And the final requirement that I want to cover before we put some technologies to the test according to these requirements, is publishing events. So event stores persist events, but then in this entire CQRS architecture, other nodes in the entire system must consume these events as well. So how to link the two? Well, the standard way of doing it in Axon Framework nowadays is with tracking event processors, which would poll the event store every second. And the reason we do that is that traditional databases don't have a way to push updates to their clients. So there's no way for us to make, say, an Oracle database effectively tell to other Axon nodes that it has a new event available. So instead we do polling, which kind of works, but it does introduce a potential delay of half a second on event delivery. Another architecture that we're seeing is that another message bus is introduced between the nodes. So whenever a node wants to publish events, the node sends it to the event store for storage and posts the same event on the message bus for immediate consumption by other nodes. Which has a benefit that it doesn't have the same delay as you would have with polling, but it does introduce the risk that the two ways of publishing the events are not atomical. So one may succeed while the other may fail. So what you want ideally is this. So whenever the event store persists new events, then they are committed to history, and then at the same time the event store should push them to readers. So everybody has immediately the right state. So that's a final requirement I'm adding here. When reading all events since a particular point in time, we also want the event store to be able to push new events to the client as it happens. So now we have quite an interesting set of requirements that we have for our event store technology choice. Let's look at some existing options. The main ones that we're seeing with AxonDB users are relational databases of any vendor we see, and MongoDB is also used. And these two options are supported out of the box by Axon Framework. The main contenders, things that we know that people are looking at or in some cases already using, are a few generic technologies. And by generic, I mean that they're not specifically designed for event sourcing. Those would be Kafka, so primarily message bus, but you can also use it to persist events indefinitely, and Cassandra. And then there are also some built-for-purpose event store engines. Greg Young's event store is mentioned most often. We had some questions on that based on the previous version of this webinar, so now we're including it explicitly, so I'll say a few words about that later on. And PumpkinDB is a project we have noticed and is occasionally mentioned in this context. Let's start with relational databases. So they have some obvious pros. They're very well established. They have very good transactionality. All the asset stuff is ticked. The big downside is performance. So because of their architecture, the way they deal with keeping buffers in memory, the way they maintain indices, and the lack of time ordering in general, means that they cannot maintain the same performance once they have hundreds of millions of events in their tables. What we see with customers that are using relational databases in combination with event sourcing is that when they become very big, they do have to create all kinds of mechanisms to keep everything scalable. First of all, very big hardware, specifically tuned versions of databases. For instance, we have customers using Percona instead of the traditional MySQL because it's a little bit faster. There may be partitioning needed. So you see, once event stores become large and you use them on a relational database, you need to constantly fight the fact that a relational database doesn't have ideal performance characteristics for this application. So the major con of relational database is the scalability problem. In addition, it doesn't have a clean general way of pushing events to clients. So we have a couple of clear red boxes there. So that's why people are experiencing problems with relational databases. Mongo has its name derived from humongous, so it should be able to store many events. It does have that capability through sharding, so it can store very large volumes of data. And because it's JSON or BSON based, you might also use it to analyze events directly. So it's an interesting choice at first sight. So people have started using this. There is, however, also a very big con, and it has to do with the fact that MongoDB is a document-oriented database. And this raises the question, how do events map to documents? Well, the obvious choice, if you think about it naively, is to map those things one-on-one. So an event in the event sourcing sense would be a single document in MongoDB. The problem with that is that two events would become two documents. And if you have two events in the same transaction, then you cannot write them transactionally, because MongoDB is fully document oriented. The transactional boundary is the document, so it's impossible to write two documents in a transactional atomic way in MongoDB. So that's a big problem. So for this reason, Axon actually supports another way of dealing with MongoDB, which is called document per transaction. In this case, you would map all the events in a single transaction to a single document, and then you have at least solved this transactionality problem. So while that works, the big problem of that is that the analysis on events becomes a lot more difficult, because events are no longer, or documents are no longer representing an event in a very natural way. So you would have to always take into account that a document in MongoDB may contain multiple events. Also, there is no event push, so the same problem that relational databases have. And because of the sharding and the way it's architectured, there is no global sequence number for events, which is a hard thing to deal with. Where you have an event stream, and very naturally you want all events to be time ordered and to be able to replay them easily into read models based on that same order, which MongoDB has a hard time fulfilling. So again, number of clear red boxes. So for this reason, people are looking at alternatives which are not yet supported by Axon out of the box. One of them is Kafka. Kafka has some obvious pros again. It's messaging focused, and events are kind of message, so that might fit. And it's very scalable. It's primarily designed for temporary storage, but you can also store stuff indefinitely, so should work. Let's have a look at the issues. So suppose this is the entire event stream as you would have it in Kafka. We have visualized the payload of events here in green and some metadata in pink. And here we assume that the events pertain to 6 different aggregates labeled A through F. So if you want to read all events for event replay, then no problem, you can get them. But suppose that you want to get the events for one aggregate, say B, for processing a command on aggregate B. Then you need some way to do that. Well, the most naive way of doing that would be to read all events and then filter them, and then you get the events for aggregate B. But obviously this doesn't scale. This is in performance linear in the number of events that you have already stored. So that's not going to work as your event store grows. So what can you do with Kafka? Well, Kafka has a mechanism called topics. So topics naturally fit this bill. So you can very efficiently get all the events of a particular topic. So you could create a topic per aggregate, and then you're all set, and you can do event sourcing on Kafka. However, if we look at what topics are in Kafka, then these are logical units spanning multiple machines. Physically, we associate a topic with one or more partitions. So partitions are on some machine. And partitions are again divided into segments to support very large numbers of events within each segment. Now, each partition has some associated directory, and each segment has a log and an index file. The key thing about this is that this doesn't scale well. This is perfectly fine for hundreds of partitions or topics, thousands, maybe millions, definitely not. So if you look at scalability here, the extreme scalability of Kafka is actually in terms of the total number of events. There's no argument there, but it doesn't scale well in terms of numbers of aggregates. So if you have the very specific situation where you have hundreds of aggregates and billions of events against these aggregates, then Kafka may actually work. but almost nobody is in that specific situation. In most of the cases, aggregates tend to be quite short-lived, with dozens to hundreds of events per aggregate, and therefore millions of aggregates, and then Kafka is just not a good fit. Cassandra, other contender, known to be extremely scalable, very well suited to run in multiple data centers, has a multi-master or peer-to-peer architecture. There's one problem with Cassandra as well, and it has to do with this example that we looked at earlier. Event stores need to be able to validate sequence numbers of new events in order to guarantee aggregate consistency. So in this case, we don't want to have money withdrawn twice. Now in Cassandra, because it's peer-to-peer and there's no master, what can happen is that these two events, of which just one should happen, get added to two different nodes. And in that case, with the normal settings, Cassandra cannot ensure that only one gets inserted. So if you would look at a Cassandra manual, what you would see is that an insert is actually an upsert. So the first one would go through and the second one would actually override the other one rather than being denied, which is exactly what you don't want with event sourcing. Cassandra has a feature to prevent this from happening. It's called a lightweight transaction, and you do that by adding the if not exists clause to an insert statement in Cassandra. However, this has a huge performance penalty. Cassandra will need to make 4 round trips behind all the involved nodes to make this happen, so it doesn't really work well. So Cassandra problem is that it cannot guarantee event store consistency efficiently. Either you get the performance and scalability of Cassandra, or you get consistency guarantees, but you cannot get both. Now finally, looking at already existing technologies, there are some of these built for purpose event stores. The one by Greg Young is most well known. This one is written in .NET, generally seen as part of the .NET ecosystem. We know of a few shops that use Axon in combination with this event store, but it's not popular at all. This places a very heavy emphasis on projection logic in JavaScript inside the event store. Our vision is that an event store should just store events and snapshots and be able to retrieve them. And your projections should leverage whatever technology is best for your particular queries. So it might be Elasticsearch, might be a relational database, might be Mongo, whatever is best for that purpose. We don't really believe in having projections inside the event store. A similar thing is true for PumpkinDB. It's a separate dedicated event store, which has a philosophy of implementing a database programming environment with its own Pumpkin script language inside the database, which we believe is not the way to go for event sourcing in Java. So because we didn't find any of these existing technologies really fitting the bill, we decided to build our own AxonDB. So the highlights of it are that it's built from scratch in Java. It's purpose-built for event sourcing and event sourcing only, doesn't do anything else. People often ask us, is there some underlying database system? No, there is not. We've written this from scratch and it manages files directly. It has open interfaces. Our primary interface is gRPC, which is protobuf over HTTP2. And we use that because it's really fast. We alternatively also have some HTTP and JSON endpoints. It's not tied directly to Axon Framework, so you could use it without Axon Framework. But if you use it with Axon Framework, it's a drop-in event store implementation that's really easy to get started with. It's append only by design, so we don't do updates or deletes, and that makes the database design easier and a lot more efficient. So that's one of the reasons why it's really fast. We split the event stream into segments. Segments have a configurable size, but typically in the order of hundreds of megabytes to gigabytes. And we keep all the indices and other files within a segment. So segments are kind of independent units. In addition to events, we store snapshots, which share the same timeline or global ordering, but have their, as a storage strategy, have their own segments. And within each segment, we have a very specific architecture to read the data. There are 3 files for each segment. One file contains the data as such, so that's the file we're appending to. when writing new events. Then there is the index. So the index, we only need one index for event sourcing. That's an index on the aggregate identifier in combination with the sequence number, because that's what we need to read back the events for a particular aggregate. So we keep an index in those terms. And then the third file that we have in there is a Bloom filter. So Bloom filter is a probabilistic set data structure. So we can ask it whether or not a particular aggregate may be in this segment, and then the Bloom filter says either no, it's definitely not there, or maybe it's there. Please check the index. So it's not a perfect set, but it's extremely fast and has a limited size, so it's easy to keep. So what we do whenever we read data or try to find events for a particular aggregate, we first check the Bloom filter. If it says maybe there, we check the index, and then we access the actual data. And this makes it really fast in this for this use case. Searching of events always go backwards in time. We start with the segment that's currently open, the one that we're appending events to. And then if we didn't find event 0 for an aggregate there, we will check the previous segment and so forth, which optimizes us for this use case of reading recent events. So these aspects that I've shown you now together make sure that we have constant performance. This is some benchmark we have done. We've actually done some larger ones as well. What we see here is that when relational database performance deteriorates as storage grows, our performance stays constant. This is true until 100 million of events. It's also true when you take this to 1 billion of events or 10 billion of events. It really doesn't matter because it's inherent in the architecture. The actual numbers here are less interesting, we think, than the shape of this chart. When you tweak your relational database, you can make it faster, or you can add more memory. That influences where exactly this curve will find itself on the chart, but it will not fundamentally alter the shape of it, and the problem that at some point performance will deteriorate, because that's inherent to the technology. We've implemented ad hoc querying, so there's very rich support for that, both through graphical interface as well as through an API. So here we see a table of events, including their, in this case, XML payload, and it can issue all kinds of filters on that. So in this case, I've filtered out payload types issued events. So I'm looking at one particular type of event where, in this case, gift cards have been issued. But the query language is actually a lot richer than this, and I can pipe this output into new select statements to project certain data from it. In this case, I'm specifically interested in knowing the time, and using some XPath here, I can actually look into the payload data as well, and in this case, retrieve the amount XML element of those payloads. This doesn't perform well for regular usage. So you don't want your end users to be accessing data in this way, but for ad hoc access, debugging, and support, this is a really valuable feature to have. Clustering is of course really important. You want high availability for your event store. We have a clustering model which is based on having a single master. But that single master is floating. So usually clusters would be 3 or maybe 5 nodes. One is the master. If a client accesses a node which is not a master, that node will tell the client, please go to another node, which is the master. And whenever the master receives an event from the client, it will immediately replicate that event towards the other nodes in the cluster. And it will report the event back to the client as being committed as soon as a quorum of nodes, so at least half of them, have acknowledged the event to the master. So this guarantees the durability and the availability of the data. Suppose that node 3 goes down, in this case, the master, then the other nodes will find out, and they will start a leader election process, and one of them will become the new master. So that happens entirely transparently, of course. So the primary availability strategy of the event store is this clustering. In addition to that, it's of course also possible to create backups of the data. And there's an out-of-the-box feature that supports doing incremental backups on your event segment files to make that a feasible process. Suppose that you want to get started with this yourself. The best way to get started is to go to our product page. Here's the exact URL, but you can also find it by going through to the main site axonic.io and then choosing the products menu. It has some detailed information about 4 different editions that we have of AxonDB. And one of these editions is the developer edition. So the developer edition is free to download. Its core limitations are that it's not supporting clustering, and it is limited to storing 1 GB of data. So we intend that to be used by developers on their own machines when writing applications, or for some initial exploration of the features of AxonDB. But it's not really intended for production, although you could use it for production if you wanted to. This developer edition, it includes the full user manual. So if you're interested in getting the manual to examine all kinds of details about the product, starting by downloading that edition might be a good starting place as well. The other editions that we have are a standard edition, a basic edition, and an enterprise edition, but the entire feature matrix can be found on the website. Now, of course, if you want to start using this, you need to run the database, which is very easy. You download it and then you run it, and then it runs. It's being designed to run with out-of-the-box settings in an open way, so you don't have to configure anything, but you can configure a lot in security terms and storage terms. Of course, you also need to do something in your application to make it talk to AxonDB. Now, assuming that you have a standard Axon 3 application, changes are actually very limited, and I can fit them all on one slide. You start by including the AxonDB client in your application. Now, the AxonDB client is open source. AxonDB itself is a commercial product that you have to download to our site. The AxonDB client is open source Maven, so you can just include it as a dependency, and Maven will find it. Then you need to configure your application, assuming you're using Spring. It looks something like this. We have to configure 2 beans. One is the AxonDB configuration bean, which picks up all kinds of configuration properties from the environment. And then we need to tell Axon that we have AxonDB event store as our event bus. And then, of course, we need to have those configuration properties themselves as well. Typical initial configuration, it looks just like this, saying, hey, I have a locally running event store on port 8123, which is the default. So that's actually very easy to get started with. So you can give it a spin in literally just a few minutes to try it out. That's what I wanted to cover for today. So again, there is a product page with a lot more detailed information. I also wanted to quickly remind you of an Axon Framework training that we have next week, and for which we still have a few spots available if you'd be interested in that. So we can take some questions now.